Hi, my name is Bill Zhao.
Jones.
This is our kinematic design and beam co-alignment lab.
We use the principles of kinematics to align beams to optical rails to one another and align components to those rails using these beams.
The first part of our lab was aligning our laser beam. We had to, in order to do the other sections, we had to ensure that our laser beam was parallel to our table and positioned 200 millimeters above it. To accomplish this, we first mounted two optic rails end to end to form a single long rail. We next mounted our laser onto a 1D translation stage and a height adjustable tip tilt mount. This enables us to control laser height, lateral position, as well as the laser tip and tilt. We first decided to get the laser to correct position. To do this, we placed an iris onto the rail and moved as close as we could to the our laser. We then used our aforementioned tools to adjust the position of the laser beam until it went through the iris. This indicated that it was 200 millimeters above the optical table. To adjust the tip and tilt, we moved the iris to the rear of our optical rail, and we used our tip tilt mount to adjust the direction of the laser until it went through the iris. We then repeat this process of moving the iris and slowly adjusting the tip and tilt of the laser beam until the laser beam went through the iris, irrespective of iris position on the rail. This indicated that our laser beam was indeed parallel to the surface of the table. Next, we had to determine if the optical table was parallel with respect to gravity. To do this, we used a beaker and a pentaprism. We used the pentaprism to reflect the light downwards onto the water in the beaker. If the table surface normal was parallel with respect to gravity, what back reflection of the laser beam will go straight through the pentaprism and back to the iris without clipping it. Unfortunately, this did not occur as indicated by this red dot here, which indicated that our table was not parallel with respect to this gravity. Next up, we used third optical rail to get our beam splitter in the correct rotation. To do this, we mounted the third rail perpendicular to our first two rails, and then we placed our original iris onto the third rail and moved it back and forth while adjusting the rotation of the beam splitter. We were eventually able to get the laser beam, or the beam splitter, facing the way that the beam would only move up and down uh, the iris, and you will explain why in the next section.
So to co-align our visible lasers, we're going to use the same iris so that we can establish vertical alignment, use a pentaprism and cube beam splitter to combine the beams, and then test our alignment through overlapping beam position at both a near and a far location. This used very much the same parts as before, except we used two lasers, strangely enough. We originally had one laser pre-aligned from the previous experiment and aligned the other one in the same method. We added the cube beam splitter to the second rail and the pentaprism to the first, such that we could get both beams emerging from the beam splitter. Using the screen near the beam splitter, we translated the second laser until they overlapped, and using the far screen, the wall, we tilted the second laser until they overlapped. We repeated those last two steps until both lasers overlapped at both spots and they were co-aligned. There is a note about the beam splitters. The beam splitter cube is not a perfect cube. Refraction at cube faces means that perpendicular incoming beams do not exit at the same angle. Uh, and that means that co-aligned outputs and perpendicular inputs are mutually exclusive. Our beams were co-aligned, which means that they were not parallel. This is shown here through the two outputs of our beam splitter. The first one is emerging from centered top left. The second one is emerging from the top right and is farther out.
The next section of our lab was aligning our lenses. To align the lenses, we essentially placed an iris and the lens onto our rail. Then to align that, what we did is that we adjusted the tip tilt of the lens until the laser back reflection from the lens's rear and front side showed up on the iris. Once we did this, we more finely adjusted the tip tilt of the lens until both back reflections shot through the iris. This indicated that the lenses was now parallel with the laser surface, with the laser's optical axis, and we did this for all three lenses. We could show you what we did here, where we adjusted the tip tilt of our lens in order to get the laser beam back reflected through the iris.
So to move on to a full system alignment, we aligned a microscope with our laser. This requires that the original beam center should not change when you add the microscope, that the microscope crosshairs should be aligned with that center, and that this shouldn't change as the microscope is moved along the optical axis. We used very similar parts as before, except the addition of the microscope with its own tip till mount on here and a sticky note on the wall so that we're not drawing on the lab walls. We aligned the laser as above and did not touch it afterwards, and marked the position of the beam. Our microscope was placed on the rail and positioned coarsely until we can see the output, crosshairs, and spot, and that the height was correct. We then translated our microscope left and right until the crosshairs were centered on the sticky note, and then rotated it until the spot was centered. We then moved the microscope to another spot on the rail and repeated those steps until the crosshair and spot position did not move as we moved the microscope down the rail. Notably, translation mostly changed the position of the crosshairs, and rotation changed pretty much only the position of the spots, which makes sense given what is exactly being imaged at which point. Our sticky note fell off the wall, so even though it looks like we are not aligned with our original beam center on these images, it is aligned with the axis. We just have a misaligned sticky note. Adding a lens to the system changed the spot magnification, but not position, as expected for a centered beam and a centered lens. Uh, and the rails themselves were slightly misaligned, so as we moved the microscope down the rails, there was a jump at the rail joint.
The last thing we did was an alignment challenge where we had to use a mirror to align the laser beam so it shot through a pipette. As you can see, we were able to do this, and we did this in 3 minutes, 12 seconds. Thank you for watching.